Welcome everyone. So this is a very special and rather unusual event. Spacetime has always been about digging towards the deepest layers of reality. For nearly 100 years, it's felt like we've been hovering just above the bottom layer. And so my friend and colleague, Brian Keating, and I decided that the fun thing to do would be to bring together today's frontline researchers in physics, experimental and theoretical, for a real conversation. So now, Brian is a distinguished professor at the University of California, San Diego, director of the Simons Observatory, and host of the Into Impossible podcast, where you will find the craziest line of the most incredible guests. So please check that out. He's also the author of the book, Losing the Nobel Prize. So if you want to know more about Brian and his amazing work trying to understand the origins of the universe, that's where to look. So, Brian, thanks for joining us.
Yeah, thanks, Matt, and thanks to the whole PBS Space-Time Studios family out there in cyberspace. This has been a dream for me to talk not only with Matt and his team, but also with my good buddies. Today we have Stephon Alexander, who I've known for, I'm embarrassed to say, what fraction of the universe we've known each other for. Max Tegmark, I've known him almost as long, and James Beacham, I'm a huge fan of, fellow experimentalist looking to solve some of the world's greatest problems in the world of physics. And today is quite fitting. It's two occasions are marked today. Well, one specifically, today is Karl Popper's, would have been Karl Popper's 118th birthday. And some say he doesn't look a day over 70. But Karl, of course, casts a large shadow over all of what we try to do as scientists. And the question is it still relevant, this conjecture, to pursue these fanciful ideas about theories of everything and whether they exist? So part of the motivation is to address that very question. And the other part is to rekindle the series of great debates that took place in the 1920s, actually in April 1920, the first so-called great debate, the Curtis-Shapley debate, which concerned what is the nature of the universe on its largest scales. And so today we now know that the universe's largest scale properties are determined in part by how it functions at the micro level, namely the laws of physics. And so these physicists who are so distinguished joining us today are going to hopefully shed some light into the nature and the inner workings of the universe and be a really good starting point, perhaps, to kick off many more great discussions this year, in the centennial year of the great debates.
Awesome. Thank you, Brian. So I'm going to bring on our guests because they have the real content here. Quick introductions. So we have James Beacham, who's a particle physicist with the ATLAS experiment at the Large Hadron Collider at CERN, and he's also at Duke University. And James is really the experimentalist in the room, and so he's going to be the one who keeps us in check. We have Stephon Alexander, a cosmologist and theoretical physicist with really a hugely broad range of interests, including string theory and loop quantum gravity. In principle, we could do this entire conversation just with Stephon. He's worked in everything. He's also a brilliant saxophonist and author of the book, The Jazz of Physics. And of course, we have Max Tegmark, a theoretical physicist with an extremely broad background also. So he's worked in fields from cosmology to the foundations of quantum mechanics, and now actually working deep in the field of deep learning. And he's the author of multiple books, including Our Mathematical Universe and the recent book, Life 3.0. So, hi everyone. Thanks for joining us.
Hello.
It's a pleasure to be here.
Yeah, thanks for having me.
Good to see you all in your far-flung isolations across the globe. So we have a lot that we need to talk about today. You know, we're not going to necessarily solve the theory of everything or even fully solve what the problem is in our search for a theory of everything. But I feel like we might be able to make a little scratch today. Before we actually get deep into that, I thought it might be a great idea for us to set the stage, and really talk about what we mean by a theory of everything and the related terms. And I felt that the most unbiased person to do that is probably you, James, as an experimentalist.
I'm happy to do so. And in fact, let me say that I think, I want Brian and Matt for putting this fantastic discussion together, because it couldn't be more timely. And the reason, if you ask the question, what is a theory of everything? Why are we here to even talk about this? It's a really good question, because down deep inside, the answer to that question is related to the fact that physicists, for all of us, we seem sometimes kind of stuffy and nerdy and very kind of analytical. Deep down inside, we're very, 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 very frustrated for the following reason. We have two completely fantastic, wonderful theories, models of the way that the universe works in very fundamental ways. So as you know, physics is the study of the fundamental laws of the universe, the way everything works at its most elementary possible scale. And we have this one theory that is called quantum field theory, based upon quantum mechanics and special relativity, that so accurately describes everything that goes on at the smallest possible scales, the level of individual uncuttable particles. It's so fantastically good that it's wonderful. It makes your kind of brain explode at how good it is at modeling and predicting things that go on at the smallest possible scales. And it's basically passed all of our tests, this particular thing that we call the standard model of particle physics. It's passed all of our experimental tests so far, and it's the best description that we have of reality at its smallest possible scales, again, in terms of particles. Simultaneously, we have a completely wonderful theory of something called general relativity, which is the fantastic description of the way things interact at the largest possible scales, the scales of galaxies and superclusters of galaxies and the largest things in the universe. And that's a fantastic theory, of course, developed by Einstein, and the mathematical properties developed by some other people at the same time, over 100 years ago. And that's by itself a wonderful, fantastic, again, it's just like chef's kiss wonderful in how good it is at making predictions. For example, as you know, one of the predictions of this theory from 100 years ago was this notion of gravitational waves. And these were only verified experimentally just a few years ago. So it keeps winning over and over again in terms of how good it is as a theory. So you take these two things, this realm of the largest possible stuff and governed by general relativity, and you take the realm of the smallest possible stuff, the quarks and gluons and electrons and things that make up you and everything around you. And you think, there must be some way that these talk to each other. There must be some way that they fit together to make a sort of theory of everything. And when you do that naively, remember, these are two fantastically wonderful pillars that by themselves are just phenomenally good. When you try to marry them together naively, everything breaks. You get crazy answers that indicate that something has gone horribly wrong. Things like infinite energies or probabilities greater than one. These kinds of things indicate that there's something wrong with your theories. So that leads us to a state that the field has more or less been in for, 80 years or something, where we have these two pillars, which are wonderful. And physicists are humans. And so we start thinking to ourselves, there must be some way that they fit together to give a broader description, a more general, a more fundamental description of everything by putting these two things together. And so far, we have not found the answer to that. And so, that's sort of just broad strokes about what we mean when we talk about a theory of everything. We can go into some more details about what that means. The notion of the forces of nature kind of unifying together, and then the three forces of the standard model going together and unifying with gravity. But that's more or less what that's more or less to set the stage as to what it is when we talk about a theory of everything.
Fantastic, James. That, I think, covers it. Okay, so we're done here. Well, not quite. So, we have a lot to get into, but what I would really love is for perhaps the three of you to talk about what you think is the state of the field, just in a few minutes, like your first impulse when we talk about where are we in this great search, and possibly your instinct for a future direction. I should also add here that we're expecting Lisa Randall to be joining us today, but she has professorial duties. She has some teaching duties that have got in the way, and this is really the most truest insight that any of you will get into our lives. Our teaching tends to take us away at a moment's notice, but she will be joining us next week, and we'll have more details of that soon. Okay, so maybe Stephon, would you like to take it from here?
Yeah, thanks, Matt. It's a real honor and pleasure to be joining. I'm actually a big fan of Matt's. Actually, you happen to think, and good to see that you and Brian are doing this. I like to say Brian's, they're going to be the next Carl Sagan, of our days. Got the skills going on there. Um, so yeah, I mean, where I can come in is that I work in, at the interface of particle physics theory and cosmology theory. So going back to what James' wonderful presentation and overview of kind of particle physics being the realm where we are probing the smallest distance scale and nature at the smallest distance scale, and cosmology is a science where we're looking at things also at the largest distance and the oldest times, time scales. Quantum gravity is a realm where we're trying to answer both of those questions. Mysteries. Um, Observational mysteries, actually, observational anomalies in the realm where particle physics overlap with cosmology. So that's some of us refer to ourselves as particle cosmologists. And I, being a theorist, I have to engage with quantum gravity. And my take on this is that I've always come to that with from the perspective of um, I would say inspired by my big inspiration is Richard Feynman, which is you have your puzzles in physics, and then you go to whatever toolkit you have available, and you're kind of agnostic about that toolkit. So I'm not married to any approach to quantum gravity or any approach. I mean, when it comes to theories that have yet been tested experimentally. So as a result, I've worked on both. I've published both in loop quantum gravity applied to problems in cosmology and particle physics, as well as string theory applied to cosmology. So let me just kind of lay out my perspective on both approaches from a more general take. And it actually starts back with Albert Einstein. I think the big contribution Einstein made was in terms of modern physics, and of course, this was applied to general relativity and special relativity, is a principle of invariance. The idea that there are underlying symmetries, in this case, symmetries that leave the speed of light the same value for all different observers, in that case, for special relativity, or symmetries under any change of coordinate systems, the principle of general covariance, which is nothing more than an invariance principle. And this principle kind of lived with us under the guise of symmetry. So that has really dictated a lot of fundamental physics, leading to string theory itself. So string theory really is driven by this: the idea that as we go to the shortest distance scale, we are to expect to see more and more symmetries unveiling itself. And so that's kind of one philosophy or take hypothesis that has driven research in string theory, or things you may hear about supersymmetry, for example, which is a kind of part of string theory as well. But there's another thing in string theory that I think I think that's interesting, which is that in string theory, you don't start off with a theory of gravity, right? String theory is an approach to try to combine ideas of gravity with quantum mechanics together, as James pointed out. And the idea in string theory, in a nutshell, is that you start with instead of a point particle, you start with a string, and the string has certain symmetries associated how it moves about, and then you quantize that theory. And when you do that, and you try to keep quantum mechanics consistent, the assumptions you made about quantum mechanics pops out of that equation, gravity, quote unquote, albeit in 10 dimensions and supersymmetric, pops out. General relativity in that guise pops out. Now, it's the wrong theory of gravity, I must add, right? But in that sense, string theory, starts with quantum mechanics and an assumption about certain symmetries, and gravity emerges. And I'm going to use that word from Max to maybe chew on a little bit. But loop quantum gravity is another approach to quantum gravity that tries to, again, similarly combine quantum mechanics with relativity, but it does it in a different way. Like what loop quantum gravity does, it says, let's take general relativity as it is. Let's take Einstein's theory of general relativity. Good old that works. It works. It explains it predicts gravitational waves and black holes, all these zany things that have been observed experimentally. It takes general relativity and it says, let's quantize that. Let's apply the laws of quantum mechanics to general relativity. And there is a caveat I'm going to say. If you do this, you're going to run into a problem. But anyway, they can succeed in kind of doing this. And then you get this theory called loop quantum gravity. And that's both theories. They're both incomplete. They're both limited. They both have their own strengths and weaknesses. String theory is a lot more developed. There are many more people that have worked on string theory. You can do a lot of cool model building with string theory. I've certainly done that. Loop quantum gravity, there's some interesting questions connected to particle physics that I've worked on. But I'm going to now say the following thing. I am left puzzled because it seems that when you do both string theory and loop quantum gravity and you try to apply quantization, there are some unquestioned things that we assume about quantum mechanics that I think that are foundational, that I think physicists, no matter how bright we think we are and how smart and elegant and all that stuff, I think went unquestioned. And some of the problems that we see lurking in both string theory, why there are all these 10 dimensions and why we only live in 4, what happened to supersymmetry, all these things, moduli stable, all these fancy things. And loop quantum gravity, time disappears. That are very unsettling to me personally. And as a result, I've taken a step back and just tried doing other things while I wait for Max Tegmark to solve the problem. So I'm now just going to shut up now.
That's a beautiful segue. An improv master, Stephon Alexander, has always been. And now we turn to one of my favorite, most mercurial personalities in the world, who, when I met him as a second or third year grad student, helped take me under his wing, even though he's a theorist and I was an experimentalist, still am. And I said, that must be why you're called Maximilian. And he said, no, I'm just Max for now. Someday I'll be a millionaire. And Max, with all your great contributions to humanity in your writings, in your personal humanity, you're an MIT mensch, as we say. I'd like you first introduce yourself for those 10 people who may be watching out of the tens of thousands who may not know you. And then can you give us your take on where things stand, what guides you, and why you think this is such a critical juncture for physicists such as us to be discussing such esoteric topics?
Yeah, so I'm feeling a lot of pressure piled on me already here, especially by you, Stephon, who are counting on me answering all the questions. But I'm honored to be with you guys here. My favorite thing to do in a pandemic, in a very polarized world, is to talk with people like you who remind me about the really important stuff. You know, here we are, almost 8 billion of us on this little spinning ball in space, who've actually, amazingly, after 13.8 billion years of cosmic history, managed to start figuring a bunch of stuff out. And I think this is a great reminder for us all to not lose sight of the really big, important picture. So let me give you my take on theories of everything with a brief history of what I think we've accomplished and where I think we've failed. And let me also take this opportunity to attack physicist arrogance a little bit. So when we say theories of everything, we have often tend to be very circumscribed and say, well, physics is just supposed to do this. And that's what we mean by everything. And all the other things that maybe biologists and others do, that doesn't count as everything, which I find a little bit arrogant. And what happened was, of course, already in ancient Greek times, in antiquity, people were able to figure out some aspects of how stuff worked. They realized that when you throw something or a catapult hurls a rock, you can figure out the motions. Archimedes did a lot of stuff on that. But other things, they just sort of gave up on. Like, why doesn't the moon fall down? Well, presumably that's just off limits for physics. Heavenly objects obey different rules. They're perfect heaven stuff. It's just shut up, don't ask those questions. Almost a sort of censorship attitude, shut up, you're asking too much. Gradually, physicists have challenged this and started asking those questions anyway. Isaac Newton came along and said, hey, wait a minute, it's a perfectly legit question to ask why the moon doesn't fall down. What if, in fact, the laws of gravity that work on Earth also apply up in the sky? And boom, they did work. But even at that time, it was still incredibly limited what we meant by the scope of physics and everything that they were after. It was basically, if you took Newton and you had him throw a hazelnut and a grape, right? He could predict very accurately the shape in which they would fly, a parabola, y equals x squared, and how long it would take for them to land. But he had no clue why the grape was green and the hazelnut was brown, or why the grape was soft and squishy and the hazelnut was hard, right? That was beyond physics. Then came Maxwell's equations and gave us all sorts of math for colors and light. And then came quantum mechanics that we just heard about here from James and Stephon that explained actually why the hazelnut is hard and the grape is soft. And we've now gone from, after the standard model of particle physics and so much else, from the situation where physics could be applied to almost none of the aspects of the world around us except motion, to one where it can actually be applied to most of the aspects of the world around us. And it's a perfect time in our conversation to ask, well, when we talk about theories of everything, what are we leaving out this time from everything? And I actually think we should be even more ambitious than just talking about quantum gravity. And I didn't mean to use the word just there to in any way imply that quantum gravity is easy. But that's not all I think we should aspire to do. I was very inspired, like you, Stephon, by Richard Feynman, also very much by his advisor, John Archibald Wheeler, who once told me that he went through 3 phases in life. First, it's all particles. So that's a nod to your quantum mechanics. Then it's all fields, a nod to general relativity. And this third phase, it's all information. And I would argue that the important aspects of the world around us that we understand the most poorly now are actually related to information. More specifically, they are intelligence and consciousness, which I happen to think are also things that we should look at as scientists and confess that we have failed to really understand well. Some people think, well, we're screwed, just like some people thought you could never understand why the moon doesn't fall down. They think maybe we'll never understand intelligence or consciousness because somehow it involves a soul or some life essence that's just sort of beyond physics. I'm more optimistic. My guess is that that it's all just information, and that both intelligence and consciousness are simply in certain kinds of information processing that we as physicists have so far failed to find the equations that describe. We know that some information can be processed very intelligently without there seemingly being any consciousness there, because most of the information processing in our brain we're not aware of, we're not conscious of. And maybe you can also have some conscious experiences that are without there being very much intelligence there. I promise to not say anything about politics, so I won't. But so to summarize, I think when we talk about theories of everything, we should aspire to also understand more about what intelligence and consciousness is, and not just because it's important and interesting, but because actually I would argue that many of the biggest failures we have in finding a theory of everything in the traditional sense of quantum gravity have to do with us trying to sweep under the carpet the question of what is an observer really. Now, here we have quantum mechanics and general relativity. They have basically exact opposite notions of an observer. In general relativity, right, an observer is this infinitesimally light, infinitesimally small particle that has no effect on anything else. And in quantum mechanics, the observer actually affects that which is observed. So if you're not going to define what an observer is, or talk about that, or try to make a physical model of it, no wonder we're stuck unifying these theories.
Have officially given us permission to pursue any question at all as physicists. Future episodes of Space Time are going to get very weird.
Good.
More weird. Going to get more weird. So James, we may be able to ask any question as physicists, but that doesn't mean we can answer any question. I feel like you might have a more measured approach to thinking about the state of the field, constrained as you are as an experimentalist. What are your thoughts?
Well, First, I wanted to just kind of jump upon one thing that Max said there, which, and also to answer your question, because when I, as any good, especially experimentalist, I have to be sort of two people at the same time. I have to be the extremely excitable, curious, kid who likes to think about these things from a very basic philosophical perspective. It's like, what's outside the universe? How small can I cut anything? These kind of, are there more than one universe? These kinds of things. But I also, at the same time, I have to, at the end of the day, say, is this something that I can possibly ever test? And I don't necessarily mean within my lifetime, because I don't like to think about just, science as being valid only when discoveries are made within my lifetime. I think about in general, is there some idea, if someone comes up with an idea and it's not possible for me to even formulate, a coherent description of how I would ever possibly test this idea, then I am rightfully skeptical of this idea. If you know what I mean. And so, one of the things that I always think about when, for example, Max set the stage really nicely for discussions like this, because I completely agree from one perspective that the notion of consciousness and intelligence are very interesting things. And in fact, they have to be addressed scientifically. But I also think that those two concepts, honestly, to me, they don't have, I've never seen a complete, coherent, consistent description, definition of what those are that I could ever really actually test and like in a scientific way, in a physics experiment in a way. And so otherwise, I mean, what I see is something like, and I think the concept of emergence is fascinating. And I think it definitely needs to be looked into more closely. But for me, if I want to just be totally materialistic and everything, I'd say, look, consciousness is really just some complex pattern of neuronal impulses, which is based upon electromagnetism in my brain. And so in principle, I could be able to model this, right? And if I have sufficiently advanced computers, I could be able to model this at some point. And then, at some point, I should be able to, create some kind of program that could replicate this, et cetera. So this is the way that I have to think about these kinds of ideas. And so when I come to ideas that are theories of everything, I also have to be simultaneously excited and looking for the next the next big idea, the next crazy idea, the wild idea that might unify quantum mechanics and gravity, or the next wild idea that might actually take a step back and supplant those two pillars with a more coherent framework, which is what a lot of the things that Max and Lisa and Stephon have worked on in the past. But at the end of the day, I'm not from Missouri, but I'm the Missouri man. Show me, right? Show me. I want to know, I want to be able to test this thing in a way. And so to my mind, from as an experimentalist, especially working at CERN, right, is that we are currently at a really interesting juncture in experimental physics, especially experimental particle physics, is that we have this fantastic machine, the largest experiment ever built, a 27-kilometer circular tunnel on the border of France and Switzerland, 100 meters underground, the Large Hadron Collider, and we accelerate protons to 13 trillion electron volts, and we smash them together, 40 million times a second, recreate the conditions of the universe after the Big Bang, et cetera. And this was this huge jump into the unknown, and this gigantic energy reach. As you know from E equals mc squared, if nature has a particle with a mass m that's all the way up here, and we as a species have only ever built a collider with it goes up to E here, we'll never be able to produce it and measure its properties. So the Large Hadron Collider was this huge jump into the unknown with all of these things that Stephon was talking about, sort of behind the scenes things we were looking for. Things like supersymmetry particles. Speaking of Lisa, Randall Sundrum gravitons, large extra dimensions. Any of these would be fantastic answers to some of the biggest questions that we've been facing in physics for a very long time. And now flash forward to 2020, and we have found precisely one new particle. And that's really, really interesting because it's a very, very wild and fascinating and wonderful particle, the Higgs boson, which is completely unlike any other thing we've ever discovered in physics ever. But it's also weird because it's the only thing we've found so far. Again, we're going to take something like 50 times the data that we have right now with the Large Hadron Collider in the future. But as it stands now, it's strange that we have this very lonely Higgs boson sitting right here. So that makes us start to think very critically about sort of the sort of the kind of motivations for the experiments. And it also leads us to this very, very interesting juncture, because with the Higgs boson discovery, we kind of were that's like more or less we're now out. We are out of concrete, sort of no lose predictions as to what to find in particle physics experiments. Mm-hmm. And that's bizarre in a way. It's a very weird place to be intellectually, because the entire history of the 20th century for particle physics was, there was some kind of weird observation. Somebody makes a theoretical prediction and it's like, that can't possibly be true. Pow, it was true. And then somebody else made an amazing thing. And this kept happening over and over and over. And the last thing to be predicted definitively was a Higgs boson. And now it's there. But we also have all these gigantic open questions, including how do quantum mechanics and gravity work together? But we don't have any big kind of like magic bullet directions as to how we should answer this. So that to me is the kind of the crux of why this is such a a unique, weird place to be, but also exciting, because it gives us a chance to get back to our roots as kind of just experimentalists and let's just explore. Let's explore, because exploration has always paid off in the past. And so this is why people talk about, next generation of colliders and the next generation of colliders, going to as high energies as we possibly can. We can talk about this if you want, but of course the ultimate possible energy, if you just give me a couple of seconds to finish, the way to, to my mind as an experimentalist, the way to really answer this question, I mean, I'm totally okay. I completely want all predictions from string theory, so I want string theorists and, to come up with some kind of oblique way we might be able to see like a hot spot or, some poles in the CMB, or I want them to say, we can actually see this, string theory, evidence of string theory showing up in XYZ experiment at lower energies. I want these things to happen. But at the same time, we know that there's one energy that we have to achieve that would basically tell us lots and lots about the way quantum mechanics and gravity work together. And this is the Plonk energy. And as all of you guys know, if you take the basic, constants of nature, Planck's constant, gravitational constant, speed of light, things like this, these numbers that just sort of, they're there. These constants have these values, and there's no particular reason for why these values are the way they are. But if you arrange them in certain ways, they're very fundamental. And so if you arrange them in certain ways to get dimensions and of energy and length and time, they give you these things called Planck scales. And that suggests that that's the place where quantum mechanics and gravity, they have to have something to do with each other. There has to be some connection there. And maybe it happens much, much before this energy, but that's the place where it has to happen. And so this is the so-called Plonk energy. The problem with that, of course, is that with current technology, with current collider, experimental technology, it's not clear that our civilization will ever be able to build a large enough collider to reach the Plonk energy. And even if you did, you might just create a gigantic black hole. So it's not entirely clear how we get there and how we would do that within a reasonable amount of time. But that's the part that sort of, to me, is the kind of, if you want to get down to it experimentally, it's like if we were able to reach the Planck scale in a collider, that would tell us a lot. And that would be a fantastic way to, really dive into what are the experimental, evidence that we would have for any kind of theory of everything.
Yeah, we didn't set up the super chat, but had we done so, we could take donations. Just kidding. We're not going to take donations for that giant collider. But that does bring us to this question. As I mentioned earlier at the beginning, today would have been Karl Popper's 118th birthday. He looks pretty good for his age. And I want to know, kind of, are we being kind of overwhelmed by the influence of Popper in that we seek this notion of falsifiability as the apotheosis of what a theory should be testable and how it should be proven or disproven, if you will, when we lack sort of the comprehensive ability in physics to really prove things. And the question is that the best we can do? Can we only live up to Popper's demarcation hypothesis and falsifiability in terms of validating in an era when we might not ever be able to build that solar system sized accelerator, or even an accelerator bigger than the current future circular collider? So maybe we'll start with James. Go back to you. Aren't we not A, approaching the limits of experimental particle physics, and B, Are we missing things that could be hiding in plain sight? I mean, there's a huge number of questions that remain, such as, why are there 16 or so 17 fundamental particles? Where does that number come from? Why are there 3 generations? What's the cosmological constant telling us? Should those not be used as the Occam's razor, to discriminate theories from pure wild speculation?
Right. And I saw that Max had his hand up, so I think he really wanted to say something
Sure.
in what I was going to say. Max, do you want to say? I'm happy to answer
Max,
the question.
why don't you go first, Max, and then James?
Oh, just a relatively quick comment to the interesting stuff you said there, James, about consciousness and show me. I'm a big Popper fan, so happy birthday, Carl. First of all, and second, I think the reason that artificial intelligence has gone from being science fiction to being actual science with real conferences and real money and real companies and so on is exactly because this field has succeeded in showing you stuff. Feynman, who Stephon brought up, right, used to say you only understand things once you can build them. So if someone thinks they understand how to make a machine that's intelligent enough to kick your butt in chess or Go, well, you should ask them to build it. And now people have done that. So that's progress. And I also just wanted to add that I think even though it's I think we need to think about that even for addressing some of the quantum gravity questions, because you stated, and I completely agree with you, James, that it is depressing how hard it is to even envision a collider that could detect an individual graviton or give the kind of experimental hints you might want for quantum gravity. But I think in the meantime, we can actually make a lot of progress doing theoretical work. For example, if you have a theory of quantum gravity, right, then not only should you be able to have a thing, an object in 2 places at once, like in superposition, like in ordinary quantum mechanics, but you should be able to have the shape of space being in 2 different ways at once. What does that even mean? This superposition of 2 distances or 2 different time intervals, and I think to answer this, if you want to be really Popperian and be like, show me, what you need to do is say, well, okay, here is Stephon's theory, here's James's theory, here's so-and-so's theory. Let's work out what observers will actually observe if it were Stephon's way, if it were James's way, etc. And to do that, you have to say, okay, here's a bunch of particles moving around, processing information. How do they experience this? Does it feel this way or that way? Now, you're facing this question of mental processes, right? And I think, honestly, in physics, this has been just as hard often as finding the math, right? Like, if you look at Einstein, for instance. His real genius wasn't figuring out the math of special relativity, which is relatively simple, right? And Minkowski had written down a lot of it, and Lorentz before him. But rather, it was exactly this stuff of figuring out how an observer would actually experience things. Realizing that, hey, wait a minute, what this complicated equation here means is that it's going to, that this observer here is going to feel that time has slowed down. People are like, whoa, that's so weird, right? And I think to predict what it is actually going to, what observers will observe and experience in various quantum gravity theory is going to be even harder. And I don't think we can do it if we just try to sweep the whole question of what an observer is under the carpet.
Just to jump off of that and also go back to your question, Brian, I didn't want to, just to be clear, I didn't want to at all, try to denigrate any kind of theoretical work. It absolutely has to be done. I hope that I made it clear that I want all of these theories. I want all the new ideas. I want all the craziest ideas. And I think that that's really, really important, because that's why, for example, I do take seriously when somebody like, just for example, Eric Ferlindi comes up with an idea that maybe dark matter and gravity are in fact emergent properties of sort of the quantum qubit structure, informational structure of space-time, right? I mean, even as an experimentalist, with 6 years of grad school and quantum field, I hear that and I'm like, what does that even mean, right? And so I want to go deep into it and understand what that means, because it, in fact, could lead to a much more fundamental understanding of what we understand, or what we know about the universe from a very different perspective, which is, I think, a little bit what you're alluding to, Max, right? It's like when you try to recenter what it means to be an observer and try to reframe that and recognize that there's a totally different description of that. That's not just a slight tweak. It's not an improvement. It's a complete shift,
Right.
forget about Popper. Let's talk about Kuhn, right? It's an actual paradigm shift with respect to the way you view the entirety of this field. Those are the things that I think are really fascinating to think about. But at the same time, I completely agree, Brian, that experimentally, and to answer your question, experimentally, what we have to do at all of these things, and I am very much, I can't underscore enough what a fantastic time it is to be a physicist right now, an experimentalist, because we have all these amazing open questions, and there's no guarantees anymore, and so we really, we're required to think in big ways, both theoretically and also experimentally, and so and experimentally thinking big does not just mean the sort of obvious things like a future circular collider at CERN. Of course, you have to have bigger colliders. There's no question there, because otherwise you'll never be able to know what's there. At the same time, you absolutely can. You need to do these other experiments too, like really nailing down the cosmological constant, really doing precision measurements in all different types of lower energy machines, right? Because the standard model is this wonderful sort of like brick that has all these wonderful predictions that come out of it, and it makes all these really precise predictions. And basically, all of them have been verified, except there's a lot that we never even bothered to yet, because it's like we just assume they're right because it's been right about everything else. But that's really where the new portal to some brand new discovery could be. We have to really hammer at the edges of this thing too. So I think that all these things can happen simultaneously. I don't think we should limit ourselves as a species to only doing, it's like, well, I'm going to build a 100 kilometer, 100 TeV collider, and that's the only thing I do. Yeah. Absolutely not. You got to do everything.
Why stop there? So I want to turn this to my friend Stephon. Stephon, as I said, it's always held up that this falsifiability is sort of as sacrosanct as Gödel's incompleteness theorem is in mathematics. And I've had this discussion with you, with Jana Levin, even with Eric Weinstein and others. Are we holding up Popper to this unrealistic, standard, golden standard? I know, Max has a little doll like I have of Carl Sagan here. He has a little thumb doll of Karl Popper that he puts on and still plays a heck of a violin. But I want to know, Stephon, are we really, kind of worshiping at the altar of Popper? And yes, to give the dead man his due, today's his birthday. But let's address this question. Is there too much emphasis placed on falsifiability? And maybe, as some say in the comments and elsewhere, we should be looking beyond Popper to a post-Popperian assessment of what constitutes science. Can it only be falsifiable science that, quote unquote, counts?
It's a very tough question. So I'll just give my spin on it, no pun intended. I do think that that criterion, for the nature of the issues that we deal with, and we can even see some of this immediately just by looking at some of the problems faced by in quantum mechanics itself, that standard is too much. And I definitely resonate. I never used to, actually. I used to think Max was a madman, not Mad Max, but we go a little way back too. And but actually I've grown. I'm not sure Max has his own opinions about me, but I would say that I've grown sympathetic to Max's point of view, and the real challenge will be actually to James and his colleagues of how then do you, if you relax the constraints of of Popper, that science should be falsified. What you define as science, the scientific evidence, should be falsifiable. So let me give an example of this, actually, and I want to throw this out for us, maybe to my colleagues here to discuss a little bit. The measurement problem in quantum mechanics and the Young's double slit experiment to me was a quintessential example of this. And let me just say a few things about that very quickly. The experiment, right? You can do it. You don't need to go to high energies. I did it in my intro physics class with the help of our lab assistant, our lab tech last semester at Brown. And the basic experiment is there's a modern version of the experiment. You have like, a wall, right, with two little holes so that particles can go through the holes. And then you have a screen that collects the particles at the end. And you shoot one electron at a time, and the electron, you can do this with light as well, with photons. And then what you see is that the electrons deposit themselves as particles on the wall. And so you're like, oh, that's good, because the electrons, will go through one hole, go through another hole, and it will be blocked by, the rest of the wall, and then you'd see all these electrons build up. And what you end up seeing is a wave-like patterns. All the electrons will deposit themselves and have this wave-like pattern. So then you'll say, well, that's weird because that's what waves do, not particles. And the electrons come out as particles. So this is, you say, okay, let's go to look to see where the electron goes. And when the observer goes to look to see where the electron goes, the wave-like pattern just disappears completely. So this is weird. And then you say, okay, you go back to quantum theory, and you say, quantum theory, tell me, to explain and predict the role of the observer in doing this. And up to today, we don't have a post-Popperian explanation to this. Now, I do know that Max is, with my friend Anthony Agrier, has written some papers about having certain interpretations of this, where you get multiple, you have to expand quantum mechanics to having multiple copies of the same, of Max Tegmarks, right? The so-called, Max, I think your advisor was John Archibald Wheel as well, right? And
Back when I was a postdoc in Princeton.
and right, and I think that, so anyway, let me just throw this out to say that for me, I'm already convinced that even like, the double slit experiment and other things that quantum mechanics and ordinary quantum mechanics presents itself. Let me also say that those things are also magical features of quantum mechanics that we use to try to build quantum computers today. But they're very weird, and it seems that, like, to really try to understand those things, you kind of have to relax the rules about, in this case, the role of the observers or what sets of assumptions that we're making. I don't claim that I have anything more to say about, as a theorist, about how to address that, but I kind of want to throw it out there to say that I think we've already entered into that realm. So let me just stop right there with that.
Sure, I am a great fan of Popper, but hey, we can always upgrade things a little bit. If you just take the simple-minded point of view that every theory is either true or false, and the whole purpose, the definition of a theory is so that it can be falsified, like Popper said, then in that case, the theory that Newtonian physics is really just as bad as the theory that Earth is flat. They're both false. They've been falsified by data, right? But that doesn't seem quite fair to say. So in what sense is Newton's gravity better? I told you, I mentioned before, John Wheeler, right, in his final phase of life, that it's all information. I think actually information theory is another alternative way, gives you an alternative way to define what you mean by science. Very loosely speaking, I would say a theory is something is good science if you get more out of it than what you put into it. For example, I found this book once in the University of Pennsylvania library. It's about this thick, and it had over 100,000 numbers in it. They were measured wavelengths of light coming out of all sorts of different atoms, all right? And it just hit me that all those numbers can now be calculated super accurately from just 3 numbers by Stephon or James using the Schrödinger equation. That's data compression if you're a computer scientist. It's even better than gzip -9. It's amazing. You got so much more out of quantum mechanics than you put in, right? Put in 3 numbers, get out 100,000. In contrast, if you try to predict the 32 fundamental constants of the standard model using some new model that itself has 1,000 parameters, that's pretty unimpressive. And it's what people in AI research would just call overfitting. So you can make this into a definition of scientific theories if you want, and say that if having the theory lets you compress the data set, so you can describe the data set plus the theory itself with much less information, much fewer bits than earlier. Hey, that's progress. So, and in that sense, Newton's gravity was enormous progress. Sure, it didn't describe things perfectly. It was ultimately wrong because it didn't include relativistic effects. But we become sufficiently humble in physics now anyway to acknowledge that probably every single theory we teach in our university courses anyway is just the approximation for something else, right? Quantum gravity or whatever, something else that we don't have yet. So I actually think this information theory way of looking at it is more true to the spirit of what we actually do as scientists. And it also gives kind of a way of thinking about children as scientists and as in general brains as scientists, because we have the brain exactly in order to be able to make predictions about the future, right? Where to find food, where to not get eaten by tigers and stuff like this. And it's not hard to prove that the key to making data compression, that if you have too little space free on your hard drive and you run one of these programs, what it always tries to do is predict what the next stuff in your file is going to be from what it's already read, and then it can store that with much less space. So if you take the just general definition of science as being able to make better predictions of the future than you could before, then I think you, James, are happy because you're making predictions. And but it's not as rigid as Popper, that you would reject things just because they're not perfect.
Turn to James to address some really fast and furious things coming in the comments. So we physicists are very fond of swag, and if you go to and enter the PBS Spacetime website events, you'll be registered to win swag for next time, and even books by our guest next week. But here's an example of swag. So this is my official Simons Observatory cap, and we put on it its coordinates. So we put on Cerro Toco, Chile, 5,150 meters. And this is 2020 edition, so it's fresh off the printing presses. I've often heard it said, what we really want is an equation that fits on a T-shirt, or perhaps next year, 2021's. Is that a legitimate goal, or is that just a cute trope that allows physicists to get away with saying funny things? Stephon, yeah. Sorry.
Wear my CERN T-shirt that has the standard model Lagrangian on it. Yeah, please. Sorry, go ahead,
Go,
Stephon.
Steph. Yeah, take it away.
So I don't think I always like I have a very strong opinion about this. I don't think that math is going to completely capture of the fundamental. If there is a fundamental theory, it's just going to be just math. Math has played a role, but math is a tool. It's a language. It's been very convenient. But I think we're going to need more than just math. Like the same way we rely on intuition and then math, to come up with a theory. Sometimes, and I can tell you about an interesting Feynman story I learned from my friend Jaron Lanier, one of the pioneers of virtual reality, of how Feynman was doing physics near the end of his life. He's not using math, okay? But the point is, I think math will be part of will be a good, useful tool. But this idea of shut up and calculate, and that finally the final theory of everything will be a set of equation or one equation, I have strong feelings about it. I think that'll be part of it, but there's going to be other tools that we're going to have to draw from. And I don't know what that is. It might look a little bit like what Max is pointing to. We probably need some observers floating out there, what have you. But so in a nutshell, I don't think math is going to be the only thing.
So we find ourselves with the experimental floor dropped from beneath our feet, and we're trying to navigate in this realm of pure mathematical and theoretical, landscape. But we have this guide. Certainly string theory has followed this guide of, following the beauty, following the symmetry and the elegance. And we've been doing it for such a long time. Even Paul Dirac said that it's better to have beauty in one's equations than to have them fit experiment. Which by that I think he meant that experiments can be wrong, but if your equation is ugly, it's definitely not right. But surely that's telling us something. Why is it that this mathematical elegance leads us so truly, even if it does sometimes lead us astray? I'm happy for anyone to address this, because I would love to know.
a lot of the things we've been discussing here. And I think that at the end of the day, I, in fact, have a slightly different perspective on this than you might expect from some, experimentalists. I'm not strictly, a Popperian or a Popperite, if you will. And I'm also not, because I don't think that falsifiability is the only, the main criterion that we need to rely upon for any kind of theory. For example, one of the most interesting things that I see in physics right now is this concept of a multiverse. Whether it comes from string theory, whether it comes from just inflationary Big Bang theory, this idea is fascinating. As it stands now, there's basically no way that I can coherently, define how to test that as an idea right now. There's some kind of vague ideas. There's some vague sort of possible hand-waving things, but it doesn't mean that it's non-scientific. It doesn't mean that it's not science, because we started with things that are known science, and we followed the chain of logic to arrive at this very strange conclusion that there could be, a multiverse amongst which we're only one. It doesn't mean that, just because we can't falsify it now, it doesn't mean we can't, doesn't mean we can't test it now, it doesn't mean we can't in the future. Right. And so that's related to what you were saying, Matt, because, I also think that, and this notion of that, Stephon, you're talking about, elegance of like a mathematic, like an equation that should be beautiful, and Dirac saying these things. I, in fact, am much more along the lines of, my colleague Steven Weinberg, who said simplicity is not a scientific principle. And whether or not you have a beautiful equation, whether or not you have a simple theory, it doesn't mean anything, because the universe doesn't care whether we think that its laws are simple or elegant or beautiful at all. And we have, in fact, we might say that, say the standard model of particle physics, maybe from one perspective, it's kind of beautiful, but from another perspective, it's very Baroque. It's like, why should our universe have as its gauge theory SU3 cross SU2 cross U1? There's no reason for that. It's very complex. There could be a million other choices. Why is it that our universe happened to choose this one instantiation of a mathematical set of objects to make real, and then a bunch of other possibilities I can write down are not there? So that to me is not so simple. It's not beautiful. It is. And so I would not go to I try not to rush to the notion of something needs to be beautiful for it to be, true, because, we're just humans.
May have something to say on that point.
Yeah, you raised, getting to the really good stuff here, are all the questions that we don't know the answer to. So I want to say something brief about what you mentioned about the multiverse and whether it's testable or not. And I also want to say something brief about the business of math and whether it's fundamental or not. So starting with the multiverse here, how can the multiverse get along with Popper? You say you kind of like the multiverse, but we also like Popper. It seems very untestable, right? Talking about places that are so far away that we could never go there, even if we traveled at the speed of light forever. Surely that's not testable. So the way I feel we should honor Popper on his birthday is to just give him some credit for being very clear on what it was that was supposed to be testable. He said it's the theory that's supposed to be testable, not necessarily every single prediction of the theory.
Yeah.
So let me give a metaphor before we go multiversal. Take the theory of general relativity, right? It predicts stuff that we can never observe, namely exactly what happens inside of a black hole.
Right.
Yes, you could jump into Sagittarius A star, the 4 million solar mass black hole at the middle of our galaxy, and make some observations before you get crushed, but you can never publish your results in Science or Nature or tell your friends, right? So does that mean we shouldn't take seriously that prediction? Well, no, because general relativity also made other predictions that we can test, like the perihelion shift of Mercury, the bending of starlight around the sun, all sorts of general relativity stuff with LIGO and gravitational waves, etc. So what we've done is we've tested the theory many times. We agree that the theory is science, and if we choose to take it seriously, we have to take seriously all the predictions of general relativity, not just the ones we can observe. And I think it's exactly the same way with the theory of inflation. If you take seriously Alan Guth and Andre Linde and the others, the theory of inflation, and you also take seriously the idea that the quantum gravity has more than one solution corresponding to some sort of uniform space with stuff in it, then inflation tends to generically predict that you're going to make lots of space, typically much more space than we can observe, and kind of uniformly full of stuff, starting out in all sorts of different ways. Can we fly away and see the nearest parallel universe, where Max Schmegmark is talking with James Beacham and Stephon, Alexander. No, of course we cannot, right?
Are those their super partners? Are those their super
Fortunately,
partners? Did you use S?
also predicted a whole bunch of other stuff that many of us, including you, Brian, have worked on measuring, like the curvature of space that's supposed to be omega is total is supposed to be 1, and it's 1.00, etc. to test it to better than 1%. So it's stuff. So this is how I think we can reconcile the multiverse with Popper. The ultimate reality out there may be much bigger than we can observe. Fine. There's no law of nature saying we should be able to observe everything that exists. It would be kind of arrogant to presume that, like an ostrich saying, if I can't see it, it can't exist. But as long as the theories that predict that stuff also predict other things that we can test, then those theories are scientific. So that's my birthday present to Popper. And maintain his relevance in the era of the multiverse.
And speaking of his birthday, his original kind of target of his ire was astrology. So I guess what is he? What would he have been? A Libra? I forget. I'm not good with my astrology. He's probably rolling in his grave, right?
Do you want me to say something about math also, or should we go to someone else first?
Please, Max, go ahead.
So this is a wonderful question, of course. Why is it that math has been so useful in describing our world? Because ultimate math is one of the most successful kinds of data compression we've come across, right? You can write down an equation on a blackboard that can dramatically simplify your description of things. Why is that? And did it have to be that way? Already Galileo was really impressed by this, right? When he said 400 years ago that our universe is like a grand book written in the language of math. And Eugene Wigner wrote this essay in the 60s about the unreasonable effectiveness of math. And since then, you guys as physicists have just been piling it on. Now there's a standard model of particle physics. And now Einstein's theory also predicts gravitational waves and black hole inspirals. And math just seems to be more and more useful. And even all the successes of artificial intelligence so far suggests that the mathematical descriptions of this computation can actually at least kick our butt in chess and translation soon, and maybe driving cars. And so why is that? I think the truth is we just don't know, and we should be humble and acknowledge that. But I don't think it's a fluke. James, you mentioned that our standard model is actually more complicated than it could be, but to put this in perspective, it's also a lot simpler than it could have been, right?
True.
Imagine if every single electron were just different. You've discovered in your work that every single electron you've ever looked at has exactly the same quantum numbers. They're entirely equivalent particles. Like, why is that? I don't know. But I think I would posit that if there is somewhere in the multiverse, maybe in the level 4 multiverse or whatever, some other place where things are incredibly complicated and every single particle has its own separate properties and everything is just completely messy, there would probably be no versions of this program happening right there, because there would be no point in even having a brain there, right? There would be, if everything just looked completely random, you couldn't make any predictions anyway. So why have a brain? So maybe there are other regions where, for some unfortunate, where things are messier, and that's not where we are. Or maybe there is some other deep reason why things are so simple here. I try to be just very humble and at least take very seriously the fact that our universe is just way simpler than it could have been, and I think it's telling us something.
So Max, your book, Our Mathematical Universe, which I believe I have right here for sale at all good bookstores, you posit that in some sense the fundamental layer of reality is mathematical, that our universe is fundamentally mathematical, and what we perceive as physical emerges from that. I guess I have a couple of questions. Firstly, do you still subscribe to this notion?
I totally do. I should clarify what I subscribe to also, because there's a broad spectrum of views as to what to make of this apparent usefulness of math and science, right? On one end of the spectrum, you have these people who say it means nothing, it's just a fluke, math is just something we invented, whatever, get over it. And then there are a lot of people who feel that math is, for some reason, very, very useful, but it's still just an approximate description of of something which is fundamentally non-mathematical. I'm in that book sticking my neck out and taking the extreme opposite point of view, as far as you can go in the other direction. And I belong to a very small minority of scientists who think that. But I think it's interesting, regardless of whether you believe it or not, to explore the range of possibilities. And now, what do I mean by that? By saying that our universe is entirely mathematical? I mean the hypothesis that our physical world has no properties at all except mathematical properties. And that sounds just so dumb when you first hear it. Like, it just must obviously be wrong. Just look behind me here at those trees there. Like what properties do they have? Well, green, kind of leafy. The leaves are a bit squishy and soft. If you're a caterpillar, maybe they're yummy. They don't sound like mathematical properties, right? But if we look at them with your eyes as physicists here, what we actually see is a bunch of quarks and electrons back there. And what are the properties of an electron? Well, -1, 1/2, 1, and so on. And we have nerdy names for them in physics, of course. James, you would call those the lepton number, the spin, and the electric charge, and so on. But that's just the word that we humans made up, right? The electron doesn't care what we call them. The properties are numbers. And as James and Stephon will tell you, the only difference is that we know so far between an up quark and an electron and a photon are exactly those numbers. The properties are different numbers. And what about the space you see behind me here? Like, what properties does all that stuff is in? What properties does space have? Well, for starters, the property 3. Again, we have a human name we made up for it, the dimensionality of space, the largest number of perpendicular fingers you can have in it, right? But space doesn't care what we call it. It's a number. And Stephon spoke about general relativity, where we've also discovered that space has the property of curvature, which is just described by the Riemann tensor, which is a hypercube of 4 times 4 times 4 times 4 numbers. That's a mathematical thing. And also topology, which is a mathematical thing. So if you take seriously the idea that so far the only properties we know for sure, that the stuff that makes everything up are mathematical, and the only properties of the space that it's in are also mathematical, then it starts to sound a little bit less insane, I think, that the idea that maybe it's actually all mathematical and we're just part of this mathematical object.
Said God made the integers, the rest is Menschenwerk. And so maybe Sabine will say that next week, and she might even critique some of the things that we heard today. So that's just a teaser to tune in. She's a well-known opponent of such things, ranging from the pursuit of beauty leading physicists astray in pursuing mathematical beauty and elegance. Yeah. I don't think I've heard, Matt, correct me if I'm wrong, but I don't think I've heard any of these gentlemen, these physicists, using beauty for anything. So I often say, and I said to Sabine in my interview with her on my podcast, and she'll be on next week, so it's not saying it, behind her back really for more than 7 days. But all experiments are beautiful, and they may not look beautiful. But I mean, James, maybe we can say a little bit more about this this question before we start turning to some other topics. But Stephon, you're raising your finger, so
yeah,
I'll call on.
I'll say something very quick in response to what Max said, and also to address this issue of beauty, because I was exactly thinking about Sabine when Max was describing this, because it is kind of the program. If you look at all the approaches so far to quantum gravity that I've played in, they all have some level of mathematical elegance, complexity, and they touch on different branches of mathematics, some more in the realm of algebraic topology, some in the level of symmetries, Lie algebras, and things like that, right? So I resonate with what Max is saying. But I also want to talk about kind of what James also mentioned, which was the notion that beauty kind of is in the eyes of the beholder almost. Like, what's beautiful to you? There's a saying, I think, Brian, you used to have the statement, every parent, every ostrich thinks their offspring is, the best, is the most beautiful thing out there, right? So this idea of beauty also seems to have a relativity to it. So your math is more beautiful than somebody else's math. My theory is more beautiful and your theory. My colleagues at Brown, the kind of theories that they work on, if you don't work, they'll be pissed off at me, okay, to say this. But they love conformal field theory, for example, right? The math of zooming in and zooming out and everything remaining the same. So let me just say something about that. So it's more of a question, which is, so if it is the case that, there is some element of that the universe really is mathematical, how do we how do we account for the fact that it's us humans that's discovering this math? And also, I don't want to say, are we inventing the math or are we then discovering the math? Like, and where is the sort of like perspective of, this is more beautiful than the other thing, right? Because what's complicated mathematics to me is simple mathematics to somebody else, vice versa. So I just throw that out.
Beauty as another rubric, but I wonder if we can turn more towards concrete examples. There are people in the chat that are asking these. Can we comment? I mean, do we want to dip into this? It's always dangerous to criticize other people's ideas, but it takes a lot of bravery and courage to be a theorist, to put ideas out there. And some of the more kind of controversial ones seem to be in the zeitgeist of the times right now, with people such as Eric Weinstein, as I already mentioned, Stephen Wolfram, Max, and folks like Garrett Lisi putting out new theories. What is it about this time, and what is it about these theories that will allow us to really make progress? How do we get to the bottom of it, given that a future collider is decades off, if it ever happens? And so by what standards will we be judged in the future? Maybe James, you want to take that? Yeah, James, why don't you start?
Yeah, sure. I mean, just a couple of words there. So, I mean, in terms of, where we go from now, I mean, and why this is such an interesting time for really potentially game changing and very, to use a kind of provocative word, wild theories of everything that are coming out, which I say with the highest possible compliment. Again, it kind of goes back to this thing that I was talking about, the 20th century, history of particle physics and just physics in general in the 20th century, is that it was this really kind of like clockwork, progression of sort of like strange observation, cool theoretical prediction, confirmation, side prediction, confirmation, and then this, it was this wonderful, almost like a clockwork. You have these discoveries coming one after another because they have these kind of like big, theoretical hints, these flashlights. It's like, you should look over there because this is a big theoretical hint, and it's always just been right where we're waiting for it. And we're out of those again. And so and it's almost as though the 20th century was so successful in such a quick 100 years way that it got us to a realm of theoretical understanding that far outpaced our technological capabilities as a civilization, under the assumption of the standard theoretical and also experimental and technological language with which we can create experiments that can test these ideas. And that goes back to this idea of the Planck scale, right? It's like, once you have quantum mechanics and gravity, and then we put these things together in the dimensions of length and time and energy, you suddenly get, there should be something amazing happening in this gigantic energy that you probably can't reach in our civilization, if at all. It would take some other civilization to be able to come up with this energy. And so that leads to this sort of like, again, it's very strange in the human brain when we get this. It's like, but wait a minute, I want to be able to test this. I want something, where's the next discovery coming from? And there's no guarantees anymore. So, for me, like I was saying, as an experimentalist, I have to be very sort of, like sober and also just like straightforward. It's like, what do we know? Quantum field theory seems real, and we should go to as high possible energies as we can. Otherwise, we'll never know what's there, just to be explored, right? The other part of me says we need new ideas, and we need to, we need to foment more of these. And so in terms of the concrete ones that might be, it's impossible to say which one is the best one and which one's going to play out to be the true nature of reality. But, to me, it kind of goes back to, somebody mentioned Wheeler earlier. And there's this diagram that I think a lot of people have been haunted by, ever since they saw it. And I've been haunted by this diagram that Wheeler came up with in one of his, I forget which book, but it's the one where it's basically the letter U. And on one side, it's a very, very thin, part of the U. And the U turns around and then it gets wider on the other side. And there's an eyeball on that part. And it's looking back at the initial part of the U. So this is the universe that has at some point evolved someone to then observe it itself. So, we as humans are the method by which the universe is asking questions and observing itself. And that to me is, again, a sort of like very, profound statement about compelling us to not just look at the underpinnings of the current understanding of nature, quantum mechanics and general relativity, but also think very critically about what it means to be a sentient, being in this universe and asking questions about the universe itself. And that to me is, I think we could have an entire show about, the thing you mentioned, Stephon. In fact, I think it's a fascinating question. Did we invent mathematics or did we actually discover it? I think we could have an entire discussion about that question. But I think at the end of the day, how we're going to make further progress with, is it going to be like a Wolfram style thing, which again, Wolfram's approach to such a theory of everything, as I think, if you want my personal opinion, I think it's fascinating. I think it's really, really interesting. It's also really, really, really difficult to vet as a scientific community, because it's just sort of like, if it's done in secret, then it's dropped upon the world. It's like, what do we do with this? You can't expect us just to suddenly go, oh, yes, we've changed everything and now yours is the right one. It's just that, it needs some kind of sort of embedding within the physics community to really understand what's going on, and in terms of things like Garrett Lisi's ideas and these sort of more speculative ideas. Again, I think we need as many of these as possible, and we need to do we need to never really get stuck in this notion of beauty. Because just one last point on this is that, in a sense, maybe there's some things, for example, you mentioned Sabine. Maybe Sabine and I won't agree on everything, but there's certain things that I think we definitely would agree on. Is that this notion of beauty should not always just guide our physics, and especially theoretical physics, because really at the end of the day, what is science? You can argue where it came from, you can argue what how consciousness arose, you can argue we can argue about what intelligence is, but science is really, if you think about it, science is the best method that we as humans have, that we invented to more or less reduce to negligible the fact that we as humans, we love to assent to things because they're beautiful when there's not actually a pattern there, when there's not actually something real. We're very, very good at assenting to things just because it feels good or it's emotionally interesting, or, and that is not the way that, but science is like, okay, hold on. Science recognizes that humans are susceptible to this type of idea, and instead says, okay, we need a coherent and like a very robust set of rules by which we can determine truth from falsehood that reduces to negligible this human ability or this human tendency to assent to things due to beauty. So again, this is not, again, like Max, I completely agree that the leaves behind you are beautiful, but I also don't think that doesn't indicate that we can't again, reduce this tendency to negligible with science as a pursuit.
So we need to ask some audience questions, but Max, do you have something quick to follow up?
Well, it was an answer to the audience question about the path forward, and then if I can also take 30 seconds, I can answer what I think is the deal with whether math is invented or discovered. So if you think of Jupiter, we did not invent Jupiter. We discovered Jupiter. It's actually out there, regardless of whether we exist or not. But we invented the name Jupiter. We could have called it Schmupiter instead, or in Swedish, we actually call it Jupiter. And it's exactly the same way if you take, for example, Plato's 5 Platonic solids. He discovered that there are 5 of them: the cube, the tetrahedron, the octahedron, the dodecahedron, the icosahedron. Then he invented the names for them. He could have called them the schmodecahedron and the schmoob, right? But he could never have invented a 6th Platonic solid. It just doesn't exist, right? The way another planet in our solar system doesn't. So that's that. In terms of what you commented on there, the audience question about the path forward, a meta piece of advice I would give is look at each area of physics and ask who's ahead in that area, experiment or theory. If you take an area where there's a ton of theories. Theory is far ahead of data. Dark energy, for example. We don't need another theory. What we really need there is more measurements. Dark matter is the same. There's almost as many dark matter theories as there are theorists. We would really like to have more measurements to try to rule out theories and nail things down.
Yes.
Then there are other areas where it's exactly the other way around. Take, for example, the particle data book and the many things we can measure to 10 decimal places now that we can only calculate the 2 decimal places with lattice QCD, right? Mm-hmm. Great area for theorists to go into. And look at those 32 numbers that you mentioned earlier.
So Max, we should take some audience questions now because we're nearly out of time.
Yeah.
So and you guys have been asking like the really pragmatic stuff that you should be curious about. So this one's a great one. All right, we can't build a collider the size of a galaxy. So what maybe I've seen Star Wars. What is the speculated accessible experimental data that could reveal new frontiers in both quantum physics and gravity? You know, something involving perhaps neutron stars or something like that. How can we get creative? Anyone who has a thought on that? I have my thoughts.
I think looking at very high energy gamma ray bursts, for example, might give you the ability to tell the difference between different quantum gravity theories. Because even though the effect is very small when light flies a short distance, if it's been flying for 10 billion years, the effects can add up. And
in fact, I think some quantum gravity theories have been falsified by exactly this sort of method.
Yes, they have.
Different wavelengths of light seem to travel at the same speed as each other. High energy ones are not slowed down by the little loop quantum gravity facets that you might expect at those scales. So, you know, things are testable to the creative.
Mm-hmm. I think
Stephon, did you want to
dark matter substructure experiments that may be probed maybe by future gravitational lensing events. There might be interesting predictions. There are some crazy ideas on the table that people with models of dark matter. Again, I don't claim to subscribe to them or not, but the idea is like theories of dark matter that have some quantum gravity ideas in it that may predict substructure. Maybe think in future about substructure. I think also the Simons telescope looking at certain effects of birefringence might be another thing. Quantum theories of gravity seem to go there as well. Anyway.
If I can just take 2 quick things, my very, very brief opinion on what where we need to go next is that, again, like I was saying before, we need to do all types of experiments simultaneously because who knows where the deviation from expectation is going to show up. But I really think that multi-messenger astronomy, so this is looking for like cosmic rays, gamma ray bursts, but also gravitational wave astronomy, these kinds of things. This, of course, will be pursued in earnest, and it has to be. But simultaneously, the next generation of colliders, either higher energy ones or the kind of more ones where we'll produce a very, very large number of Higgs boson particles, those are going to be just more or less game changers. I mean, there's really no question whether we should have large experiments that can create a large number of Higgs bosons, because the Higgs boson is sort of like we have this gigantic standard model, which is awesome, and we understand everything really, really well, like pinpoints, but our understanding of the Higgs boson is like gigantic. And it could be this fantastic portal into possibly answers to some of these questions. So, is it the only fundamental scalar field that exists in the universe, or are there other ones that are related to it? Is it in fact composite? Is there structure inside there? Is it in fact, does it actually talk to dark matter? And also, does it have, what's the shape of its potential? And if you measure the shape of the potential of the Higgs boson very, very precisely, which is what's planned for future experiments, that'll give you a window into how the universe, in fact, came about exactly the way it did right around the moment of the Big Bang. Was it a first order phase transition for electroweak symmetry breaking, or was it something else? And also what the fate of the universe is. So these kind of things together, they sort of have to be done. Otherwise, we'll just be ignorant for decades.
We need a shout out to inflation also. It's Brian's wheelhouse here, because obviously to learn about quantum gravity, we would like to look at physics where it's both very small and very massive. So either end states of black hole evaporation or our Big Bang. And it's a real bummer that you lost the Nobel Prize, Brian. How could you? Because if you had discovered gravitational waves and you had kept them around, right? Or maybe in the future, if you do it with just at a lower amplitude, then that might
be my next
very
book.
well give us fantastic clues about quantum gravity.
Oh, that might be my next book, winning the Nobel Prize. Maybe just segueing to that, maybe Stephon, you can pick up this last question.
Yeah, I want to actually resonate with what James said. I think like my postdoc advisor, Michael Peskin, convinced me of this, that we simply don't know what electroweak symmetry breaking is. This is what James is referring to. The current standard model, that's a placeholder. And it could be actually the Higgs is also the Higgs, and discovering its true nature, which will tell us about electroweak symmetry breaking, might actually have clues to quantum gravity. We just don't know. So I think I want to resonate with what James said about particle collider physics as well.
Yeah. So last question I had, maybe it ties into a little bit of what Max was saying, maybe not. We hear a lot about the anthropic principle and maybe tie-ins between inflation, the multiverse, the landscape, swampland, all these things. Are those potential guiding, fruitful guiding avenues to understand the theory of everything, or are those likely to be a wild goose chase?
I thought that was funny. I think the one thing I hate about the anthropic principle is that the word principle is in there as if it's somehow optional, when it's in fact just the correct use of statistics. That shouldn't be optional. You know, if you write a paper saying you studied the size distribution of fishes in a pond, then your net is this wide, and you didn't find any fishes smaller than that, that paper just should get rejected. That's not a principle. I think fundamentally physics is about making predictions for what observers should observe and making experiments to see if those predictions are borne out or not. Then you just have to do the calculations correctly. And if it happens that you make a big space and some properties are different in different parts and some don't have observers, you just have to fold that into your math. Otherwise, your whole analysis is rubbish.
So we only have a few minutes left, and I wanted to, maybe end by where we should have started. Physics is great at really defining its problems, and we're quite precise, because we have math. But I do wonder sometimes if we're even asking the right question, or if we know what question we're asking. So when we try to search for a theory of everything, what are we doing? Are we asking what is the primal cause? Why is there something rather than nothing? Or are we being more pragmatic? Are we trying to find the equation that fits on the hat so that we can do all the calculations with one equation? I would love to just each of you to maybe say, what do you think the final answer will feel like? Maybe Stephon, if you'd like to start.
Well, I'm going to speculate. I think that the final answer should bring into account the human being. And the diversity of the human being, the different perspectives. I mean, I have friends who I'm also a musician, so I'm a big fan of classical Indian music. I have friends who, their approach to playing like music has a mathematical linguistic take. As a jazz musician, for example, the role of improvisation as a scientific way into creating music that ends up like John Coltrane looking very mathematical. And what's that about, right? What's the informational content of that? So I think like the various ways of bringing in the very observers, Max, I resonate with Max big time in this, how to do that. I mean, general relativity gave us hints about how to do that. I want to give a plug to my friend Eric Weinstein. He has this idea of the obserververse in his theory. So I think we should have a marketplace of ideas, but the end game, I think we'll start with us as humans, the ones doing the creation, and not throwing the baby out with the bathwater. We have theories that work and they predict things, but and I think moving forward, how do we bring all these different perspectives into what that new science looks like? How to engage each other as human beings in doing that?
Beautiful,
Max.
At the risk of sounding like Stephon and I have a mutual admiration society going here, I will agree entirely with the idea that we need to talk seriously about what an observer is. I would suggest we don't just talk about human observers. There was a very cute chipmunk that just walked under the table here a minute ago. I'm quite sure it's observing too.
collapsing
And
your wave
I
function.
think in the future we might see digital minds that we've built ourselves that can also observe. I suspect that we'll be able to find an end game where you have some mathematical equations or some computation that describes what we call our universe. And by studying it, you can not only realize that it's going to have these observers in it, but you can calculate what they're going to observe. And if it agrees with what James and other experimentalists actually find, then you can start to think, hey, maybe this is it. Maybe this is what we should put on Brian Keating's future baseball cap merch.
Speaking of merch, Matt, maybe you have a few final words, and we'll wrap up with a little teaser for next week.
I would like to hear James take.
Oh, yeah, sorry. Yeah, James, please.
Just 10 seconds with my opinion on that. I think that the final answer, if you're asking that question, I'm not convinced there is going to be a final answer. And I'm not saying that from sort of like a hippie-ish woo-woo perspective. I'm saying that the history of science has been such that it's a human pursuit of constructing knowledge and constructing our understanding of the universe in a better way and a little bit more advanced as we go along. Even if we were to discover that at its basis, the fundamental nature of reality is somehow mathematical and informational, which are kind of the same thing, then we would, and if we were able to figure out a way to communicate with a part of the observable universe or the universe that we're not within, or some other universe, even if we were come up with that would open up new realms that we would then need to explain. And I think this is why I'm not convinced there is a final theory other than humans as one version of a conscious being, a sentient being in the universe, that have come up with this way to ask questions about the place in which we happen to be. And I think that I totally agree. I would love to see what the squirrel's version of science is. I would love to see what a different, civilization's version of science is. I'm not convinced there's a final answer, but I'm absolutely loving the fact that we as humans get to ask these questions.
That's Life 4.0 in Max's lexicon. One for each level of the multiverse. Matt, yes. You want to take it away? And
speaking of books, so before we wrap up, there are some winners of some of these amazing books. I'm going to read those out now. So the winner of Max Tegmark's Our Mathematical Universe is Chris Lydiard. Congrats, Chris. The winner of Brian's Losing the Nobel Prize, Marion Edwards. The winner of Stefan Alexander's Jazz of Physics is Omer Subasi. And there are Spacetime T-shirts we have Aidan Beckley. I can't quite read that. Is this Tino Patricia?
Patrina.
My apologies. And Arbo Nuriana. So congratulations. You'll need to email us at pbsspacetime@gmail.com, and we'll get those out to you. So, Brian, any
parting words? For not having my book done. Otherwise, somebody could win my book, but it's not done yet. Sorry.
But you have finished it, just not in this particular universe.
Well, I want to thank everybody and just remind everybody out there why we're doing this, because as James and Max and Stephon have highlighted so spectacularly, it's really amazing. It's almost a miracle if you think about it, how what a time we live in and how exciting it is that we human brains can actually access some of the deeper regions of the universe and perhaps unravel future mysteries for our great grandchildren advisees to take on in their PhD theses. It's a very vibrant field, and I want to advertise next week's show. We're going to have Lisa Randall. Again, she was supposed to be on today. She'll be on next week. The effervescent Sabine Hossenfelder, Eric Weinstein, and all of us have a soft spot in our heart for Lee Smolin. He will be on next week as well. And we invite the guests to join in next week, the three of you gentlemen, and please join in the chat in case we bring something up. Maybe we'll read that out. And sign up to get notifications about that next week, and you'll receive an entry into winning the books by Sabine, Lisa, and Eric and Lee. So these are not Eric. Eric doesn't have a book either. We're going to work on that. But for now, Matt, anything else you want to say? I just had such a blast with you guys, despite two of the three of you being theorists. It was great. No, I'm just kidding. Love you guys all. Thank you so much for taking us up on this. And the audience out there, phenomenal questions. Stay engaged. We'll try to answer as many questions as we can in the next 13.8 billion years.
And Brian, thank you for helping pull this together. You guys have to check out Brian's podcast, Into the Impossible. There's some incredible conversations. Stephon, I watched through all of your conversations with Brian. I learned an awful lot. So really, just thank you all. Did we figure out the answer? Well, I think what we figured out is that the brightest minds of our time are really struggling with, at this point, the most fundamental philosophical as well as scientific questions. And if you lot can't figure it out, well, then I guess we'll never understand space-time.
No. That's why we need all the young listeners who are watching this to come study physics.
Yeah,
and help us answer it.
And watch the great resources on PBS Spacetime Studio.
Physics is not some sort of stale old field like calculus, which is all done. You just go learn. This is work in progress. And
yes, and that's true. We should mention that the videos that Matt has on PBS Spacetime, those are a really good intro to anybody that's out there. It's like, maybe I should actually think about majoring in physics. Yeah, you should do that.
That's homework for next week, actually. There's loop quantum gravity, there's theories of everything, and many other resources, thanks to Matt and his awesome team. I just look up to you guys so much. Thanks, everybody. I can't wait to see what we come up with next.
Thank you, guys.